So, thank you all for joining us. We just introduced a little movie so to get acquainted and get a little bit up and running after the lunch. Hope you all enjoyed your lunch. I'm Chris, this is Gary.
Hi.
We flew over from the Netherlands, from ING. And we're here to present our presentation called Testing the Waters, Consistency Required. Why consistency required? Because consistency is really important for us as a bank. ING is a bank. I will go onto that a little bit later. And you will hear the word consistency a lot during our presentation. We did a lot of proof of concepts during our time, the last year, just to prove that we can achieve the consistency we as a bank need with Cassandra. So especially the combination Cassandra and consistency, which is pretty hard. We have some pointers, some war stories to tell you about how we achieved consistency and actually made or got the beliefs across to our CIOs as well. So they are all with us. What is ING? ING is a bank. It started up in 1917, not as ING, but as Postbank. We are a merger, so we merged a lot lately. So we have a very complex landscape, like many banks here. We also have a lot of mainframe systems still. And we actually are front-runners in technology in the Netherlands at least. So in 1986 we made our very first digital payment. The very first bank in the Netherlands to do that. And also we were the very first one to have an online portal for our clients to actually make transactions. And nowadays we have the best rated mobile banking app. So we're still proud to be the front-runners in technology in the Netherlands at least for the banking institutions. And we think with Cassandra we can even be better in the future. So, who am I? I'm Christopher Reedijk, full. I'm a dev engineer at ING, so mainly focusing on development. I've been working in IT for almost 10 years now, or actually more than 10 years now. And for 4 years I am working for ING itself. And the last year we spent a lot of time on Cassandra. I'm more of a back-end guy than a front-end guy. There also comes more the relation to a Cassandra database than, let's say, RESTful APIs. And I always been there. So I was, in the past, I was a business process modeler or a business process analyst. And there I already made a lot of integration with the backends and had a lot of check on the backends and with which we want to go. And therefore also Cassandra is a very logical choice. And that's also where I worked a lot together with Gary on the Cassandra part at ING.
Hi, my name is Gary. I have a bit more IT experience than Chris, but a little bit less in ING. Similar background, backends, business processing, middleware, all of that. And I also have a strong database background, so this is why I tend to have a love-hate relationship with Cassandra, because you can do joins and you can do a lot of cool stuff in other databases, and you come to Cassandra, you have to give up a lot of these features, but you get something else in return. A year ago, we actually came to this summit in Europe, the London, and it was our first exposure to use cases of companies using Cassandra. So we really appreciated that, and it opened up our minds to solving problems differently. After that summit, we went back to Amsterdam and we started looking at our own problems and seeing if we can use what we learned. So this is our contribution back, so hopefully we can give it to some ideas to other people, and you'll be helping us in future as well. So it should be a community thing. For backend guys, we decided to step even more out of our comfort zone. The presentation is done in JavaScript and HTML, so we hope you enjoy it. Chris was mentioning that we have 100 years of history. What we've noticed is that the last 2 to 3 years is really changing. And the rate of change is increasing. And what does that mean? We have so many new interfaces, so many new access patterns, so much desire for the data. It's really taking the stress on our backends in a sort of unexpected way. So we've realized that we need to start thinking about things differently. We've been in the news for unavailability, and we take that personally. We really are affected by this. So we're working on alternative ways to solve this problem.
Definitely. And if you look at the major challenges we see, is specifically the 3 first ones. The 4th one was a bonus from our CIO. We have a lot of, as we already said, we have a complex landscape at this moment. So that means that we have some limits in our scalability with some systems within the ING. So what we see now for the future, with all the load we are expecting to come, even the unexpected load actually, we need to be easier scalable as a whole company. So not only on the database level, but also on the front-end level. So that's a really big challenge we have. We need to remove any single points of failure. It seems to be like an open door, but still you see that there are a lot of single points of failure in your whole infrastructure within ING as well. So it doesn't only mean that if you have high available data, that you are high available to your clients as well, right? So we have to do it top-bottom and bottom-up to make sure that we are completely high available for our customers as well. And that also means a point Gary will address later on. There are some other single points of failure to think about, and there are also solutions for that which we will address as well. And maybe the most important part is we should never trade on consistency to our clients. Clients actually make decisions based on the data we present to them. We are a bank. They should trust the data that we give them. So if we are showing them incorrect data or inconsistent data, they will lose their trust and maybe even leave us as a bank. So that is key for us. That's also why we focus this much on consistency in combination with Cassandra for this presentation as well. Now, the bonus one was active-active over data centers. It was a nice challenge. It makes it even harder to do it. And why? Because we are now active-passive, meaning that one data center is passively joining the whole infrastructure. If a disaster happens in the active data center, we have to switch over to the other one, meaning we have limited downtime. And we want to get rid of any downtime because we want to be high available, right? So how will we solve that? We will solve it with distributed systems. So why? Because we see that the big engineering companies around us are using distributed systems as well to be high available to their clients with high throughputs, with high demands. So we thought, why shouldn't we as a bank also do that? And us being back-end guys, focusing on the back-end and the database, you think, okay, what is then a distributed database? It's soon you get to the conclusion that NoSQL is the way to go. And then there is a lot available in the whole market if you look at NoSQL databases. And we came to the conclusion that Cassandra is the way to go for us as ING. And why? Else we wouldn't be here, of course, as well. So we really like the masterless architecture, especially if you look at the active part of our needs, of our challenges. We did a lot of calculations, discussions, and checked what is the best way to go. Is it masterless or master-slave? And if you really want to have an active setup without downtime, it seems to be that masterless is the only way to go. Next to that, it gives you a lot of flexibility, Cassandra. Why? It is tunable consistent. We all know that concept, I guess, or most of you know the concept. So you can tune your consistency per query you actually execute on your Cassandra cluster, which is great for us because we have multiple use cases which we actually want to execute queries on. So from the front side, we see different levels of consistency needed. The other one is for data modeling. Because Cassandra is a column family store instead of a key value store, it will give you way more flexibility in your data modeling. And therefore, it was also suitable for way more use cases which we want to use within the bank. We really love the fact that there's a huge active open source community behind this product. It really helps us, gives us trust in this product as well. We see a lot of fixes coming in. Also, if we ask for fixes, we see that it's taking up very fast by the community as well. So everybody here, thanks for helping us there as well. And thanks for giving us the trust in this product to go on with it within ING. And we really mean that, and that's why we also want to give something back. SQL3 is a nice feature it gives as well. It reminds us of SQL, which comes back to the love-hate relationship of Gary. And of course, the active support comes out of the box with Cassandra, so that's cool.
Indeed. You know, if you look at what we're doing today, we have an active-passive setup. And generally speaking, you start with synchronous replication. So what does that give you? It gives you maximum consistency. You don't have to worry about consistency, but you have also maximized your single points of failure. Any component in the chain breaks, you're out. You also have the slowest write latency because you need to do over the data centers because it's synchronous replication. Generally speaking, the first step that we'll do is we will lower that to asynchronous replication so that we can have a faster write path, and then we also have less single points of failure. But we still have the single point of failure of the link. So that was our starting point, and then we decided to have a look and see what we could do with Cassandra. To do the same thing in Cassandra, you could have the synchronous setup where you do writes on each quorum and reads on local quorum. And then essentially what you get in return for that is less single points of failure because Cassandra is designed to tolerate node loss. So now you can lose a node on either data center, but you still have the single point of the link. But we value the consistency one level lower, and we're getting into that in this presentation. Then you can also do the same thing. You can do asynchronous replication, and there you do a write and a read of local quorum. And again, because you're now able to do changes on both sides, we value that consistency one level lower. But the first thing that we were looking at this is, what's the difference between the two is that you have a single instance versus multiple nodes. So our fear was, what would happen if the times on the machines were different? How would that impact us?
It can impact, definitely, because as said, we did a lot of proof of concepts, and one of the proof of concepts actually was about how can times or time sync issues have impact on our solutions. And just to illustrate it briefly, what can happen, for instance, is if you have an append-only model, so we're inserting a new state into the first node in the cluster, which is actually living in the future. That's why we marked it red. So it gets a future timestamp, in that sense, the data. Then we do another insert with open state. It goes to another node in the cluster, because of the round-robin policy, and then it gets the normal timestamp. So if you look at the previous one, it's actually in the past. So when I do a read on the next node, and I have an append-only model sorted by date, it will mean that I get the wrong state back in that sense. So that means that I'm getting new back instead of open, which was my latest state, meaning I'm inconsistent with my replies to the customer. So that's one of the biggest issues we have seen with time sync. And why is that a problem, and how did we fix it? We fixed it with a finite state machine, but also with an append-only model. Append-only model helps here, especially if you can be idempotent in your modeling. So it means that if you append your data, you're at least not overwriting your data, you're not updating your data, so you already overcame that other obstacle that you can have with updates. So append already helps you there. And why the finite state machine? The finite state machine is a pre-configured state machine which knows from which state to which state I can go via which transition. So that actually means that if I want to retrieve my latest state and I'm getting a wrong state back, I can report back to the client, I'm getting the wrong state back from Cassandra, so there's something wrong. You have to do something about this. So this is how we can overcome problems with out-of-sync times and states coming back to our clients.
Indeed. So basically just try to avoid using time for any decision making in your process. It proved to be quite challenging in some places. We did say we wanted no single points of failure. So what actually happens is you still have a single point of failure when you have two data centers, because you've got the link. If you use quorum, then you will have a single point of failure. You can also, for the asynchronous, you have the chance of split brain. Doing an update on one side whilst reading on the other side with the link being down means you can get inconsistent data between the two, and you definitely want to avoid split brain. What can you do about it? The first thing you can do is you can do data center stickiness. This is kind of like when an order comes in or a transaction, you basically tag it and you say, this order came in data center 1 or Rotterdam. And then you only process or make decisions on that order within that data center. And if, for example, the order comes in the wrong data center, then you need to route it to the other one. There's a lot of complex logic, routing, but you can do it. Problem with the solution as well is not a full solution. You still have limited outages for the data that comes in the wrong data center. So the alternative you can do is you can go for 3 data centers. Key thing to make note of is that you need to have a link between each data center. Otherwise, you still have a single point of failure. So 3 data centers needs 3 links, so that you can always satisfy quorum over 2 data centers. So for our proof of concept, we actually started with 10 nodes, and then we had to split it down into 3 data centers because we wanted no single points of failure. So then we went 3, 3, 3. We were a bit concerned about this because we were doing replication factor, which is the same as number of nodes. That means that we're not testing for hotspots or sharding of the data, something else you want to test for. But it turned out to be a very good thing for us. We found a couple of interesting issues. Batching, for example, using atomic batches, needs a minimum of 2 nodes per data center to make it resilient. So what actually happens is a batch comes in, gets copied onto another node, and then it's resilient. So if you think you have a tolerance to failure of 4, you actually only have a tolerance to failure of 1 per data center on a small cluster. We don't really mind because we're going to be going with a larger cluster as we go down the path. But what was really interesting was when you're doing performance tests, you want to test on multiple nodes. When you make a configuration change, you will notice it immediately because all your nodes will actually react the same way. And what we noticed was when we were writing on quorum, the consistency part was all going into compaction and flushing at the same time, but also the eventual consistency part, so the nodes that were not included in the consistency level, they also went into compaction and flushing at the same time. So you can actually see eventual consistency is as fast as a normal consistency. Because we have cross data center latency and we were making tweaks, we could actually see the impact immediately, which was pretty easy for performance tuning. But the best thing that we learned was it's also easier to increase the latency. So when you actually want to find your corner situations, if you really care about consistency to a level, you want to increase the latency, you want to have the queries getting slower, and then you want to start killing stuff, because that's when you're going to start seeing some issues. We have a confession to make. We did know about this. We brushed it off and we said, it's not going to affect us. It's not a problem.
But it was, yes. And it's called post-observable behavior in that sense. So just a quick example of what post-observable behavior means for those who are not really up to speed or in line with us yet. We have 3 pictures to describe it. Imagine that I first do an insert with open into my cluster, and then it will be replicating the data to the other nodes, right? And waiting for acknowledgement on the coordinator to make sure they are written to the cluster. But before the acknowledgements come back to the coordinator, my coordinator dies. So actually my client is getting an error or a timeout and sends it back to the client. And the data center, the cluster itself already has the data. So when I do a select on my data again afterwards, I will get an open state back where I actually expected a new state because I thought the second state which I inserted was not inserted because I got an error or a timeout. So what we learned from this is the only truth is success. So if Cassandra gives you an error back or no answer at all, it's pretty much a maybe. So you have to double check if it did or did not go in there. So how did we overcome this issue? Because this is also giving us inconsistent state back. It would be beautiful if our whole application was completely idempotent. Then a simple retry will do the trick, right? Just do it again, and then it will retry the action, and then what does idempotency mean there?
Yeah. Idempotency is when you do an action on the database, there's no net change. So if you repeat the same action, there will be no net change on the data in the database.
Yeah. So that would be making it a lot simpler, right? So a simple retry would do it. But since we have an application with non-idempotent parts in it, we have to do something about it. So we have to first identify those paths in there. Most of the times it is when we have to access an external system. And what we do, we have reintroduced the finite state machine here. So we're using the finite state machine again to overcome post-observable behavior within Cassandra. How do we do that? We add a technical state before we hit or we're going into the critical path. So that means that we know for a fact that it's written. and I can do it again and again and again. And every time when it gets killed in this critical path, my technical state remains in Cassandra. So when I want to retry the same message, I will hit the same path again. And what the finite state machine does, he reads the state back, and he will get a technical state back instead of a normal state, meaning something is wrong in my application, in my data as well. So that means he marks this order or this transaction to reconciliation. So it means we either had to manually or automatically fix this order or this transaction to make it go through again how we would like to go, because we don't know what happened afterwards. So we have to investigate what happened. So those are actually the three major issues we have seen and our solutions for that. And then we have another one. It's not really an issue, it's more like a challenge you have, especially in banking. We still have batches, and I'm not talking about the Cassandra batches we all know. It's about batch files. So we have some data coming in, batch files coming in, but also real-time traffic coming in. But also we have batch files going out to external systems. That actually means that we are getting messages in on multiple nodes, and for somewhere in our complete application we have to merge it together and make sure that that one message is going out to that one external file only once, because we don't want to have it processed multiple times. So that's called the synchronization issue, and we have a solution for that within Cassandra, and Gary's going to tell you all about it.
We can just quickly have a look at what we actually do today. Today we use a transactional database, and essentially we do begin tran, select for update, which essentially locks all those rows, and then we do the work, and then we commit. That query is a synchronization. It's pretty much 10 lines of code in a transactional database. The problem with this query is it's not scalable, it's not resilient. So when something goes wrong, you need to restart, and you have essentially, as the load goes higher, you need bigger boxes. But then, of course, if we look at it in Cassandra, we have another challenge. We don't have any of these features. You can't go begin tran. You can't go for update. You can't do commit. You know, the love-hate relationship. So we really struggled with this one. We were wondering how we can do this and how we can also be active-active in the solution. And then we came up with, after a couple of days of brainstorming, we came up with an analogy called train management. And essentially, train management sort of follows into the philosophy of doing it on the writes, solving quite a lot of your problems. So what we have is, we have a train. The train is essentially the outgoing file. So, and that's going to go to a destination. The destination could be the B2B system or a backend, wherever it needs to head. And then we have passengers. And passengers can be the single unit of work, so an order or a transaction or a payment. And a passenger will board a carriage. And a carriage is essentially a chunk of the train. So that way we've split the problem up.
Yeah, and because it's very important to understand what all the parts mean in this analogy, we do see sometimes that people get a bit lost in the analogy. So just a quick recap. The train is the complete file we're sending out to the receiving application, which is the destination. And a train normally exists of multiple carriages, so that's why those are the segments of the file. And if you look at a carriage, it normally holds passengers in there, so that's an order, a message, or a line in that segment of the file. And that all together, again, makes it a complete file which can be sent off to the receiving application. So that's the main concept you need to know about this analogy.
So we're going to break it back up. Let's look at it from the passenger side. So an application owns a carriage. And you can see a carriage as a partition in Cassandra. And the application, it's one-to-one. So one carriage is owned by one application. It means if I put a little bit of state in the application and keep a counter of what I'm inserting into the carriage, I don't need to keep reading before I'm writing. So therefore, I can just push data into the carriage. What we noticed was we built in a synchronization point because we needed the last thread when the carriage is full so that we can actually attach it to the train. So the last thread is important, and the way we solved that originally was to put the synchronization point in the application. Problem was we forgot about the active-active part. So every time we were doing a query, we had to add the cross-data center latency. And that resulted in minimizing the throughput that we could do with this way of solving it. So then we we took out the synchronization point and we added another counter, and we call this post-counting counters. So that means when you're in a distributed system, you can send out 100 requests. You can almost guarantee that the 100 requests will not come back in the same order. So you don't know which one is the last one that actually came back. So we added another counter which counted the number of acknowledgements. And when we got to the same number that we sent out, we knew that was the last thread. And because we had the last thread, we could then get a lock. Chris is going to talk about the lock in the next section. But I now have a lock, so I'm able to get a lock on the train. So I'm now able to say nobody else is working on this train. So I can attach this chunk to the train. And then I still have a thread. If the train happens to be full, then I can get a lock on the destination. And then I can actually send the train out. So this way we're solving the problems on the writes by continuing with the threads as they're coming in, and when the train is full, we allow it to depart. We did have some extra problems. We were fighting for locks a bit too much, so we solved that by accumulating locks in the application. So there are extra things you can do to reduce the contention with cross data center. But if we put it back all together, you can see many applications all filling up carriages, and then as carriages are full, we attach it to the train. As trains are full, we depart the train, and then we can start with new carriages. So this way we actually ensure that we only send the messages out once and one and only time. We haven't got bottlenecks. We have a masterless solution for our batching out. If something fails, another thread can take over. You do need to think about your maintenance and your depots and all the other tables just to put it all together. And for the locking,
we introduced 3 methods. Actually, there's a nice dev blog article about it as well. It's called lease. We just found out this week. And we call it cluster lock already. And how does it work? We introduced 3 functions, basically. One is the acquirement of the lock, one is the refresh of the lock, which can be called multiple times, and one is the release of the lock. So what does an acquire mean? Acquire means I want to get the lock, so I'm inserting something in my cluster lock table. But I'm also using lightweight transactions here, right? So I can only insert the lock if no other one is already working on this train or on this destination. So using lightweight transactions, it will give me either back an applied or not. And if I get an applied back, it means I can continue on processing. I got the lock. Therefore, I can further work on this train or this destination. We also insert the data with TTL because we don't want to have infinite locks, right? But still, during processing, it could be that I need more time than the TTL I have specified up front. So that's why I need the refresh method. It actually gives me the possibility to update my TTL constantly. And it works the same as the acquirement, more or less. After that, when I'm done processing, I want to release the lock as soon as possible. So that means every millisecond counts. So when I'm done processing, I will release the lock, and another thread can pick up the destination or the train again and do the processing of that work in this synchronization form. And that's pretty much what the lock is all about. So, just recapping what we all discussed during this presentation, we had time sync issues, which we pretty much said don't use time for any decision making in your application if you're using Cassandra. If you still want to get, for instance, the latest state, finite state machine might be the way to go. It worked perfectly for us, so it might also work for you guys. We had single point of failures and split brain. So if you have a 2 data center setup and you still want to be consistent, please be aware of that single point of failure in between those 2 data centers. Workarounds could be data center stickiness or a 3 data center setup. And post-observable behavior, right? So we can have post-observable behavior. Again, we reintroduced the finite state machine here to overcome this obstacle. It might also work for you. It worked perfect for us. And it made us actually succeed in our proof of concept for our CIOs. And last but not least, the synchronization issue. We believe we have found a solution for distributed synchronization with Cassandra, and therefore we use the train management analogy.
Indeed, and if we put it all together, we think we've managed to achieve the consistency that we need for our use cases. But also the more important thing is not actually limiting Cassandra's scalability and availability. What we noticed was quite often the time we were adding the bottlenecks in our application. And it took us, just to step back and have a look at what is actually happening and where is the bottleneck, and not always blaming Cassandra or the other software. So really think about the problem and try to limit the bottlenecks in your own application. Of course, we haven't mentioned what our use cases are. We're not fully in production. We are going in the next couple of months, so we don't want to jinx it, but we are picking up the critical processes, and keep an eye on it. Thank you.
That's it. So, any questions?
You mentioned the lock.
Yeah.
You're using. Don't you have any consistency problems with multiple data centers? So, like, if you acquire the lock in one data center and another one is trying to acquire the lock in another data center at the same time, do you not get consistency issue there?
No, we have not, and that's mainly because of the lightweight transactions, how it works. It's actually acquiring the lock with a serial consistency level,
And not local
which is
serial.
already like quorum, so it's already going cross DC. So we have cross DC awareness of this lock by default, using the lightweight transactions.
And with the train management, we reduced the number of lightweight transactions by a factor of 1,000, because for every carriage, basically if the carriage size is 1,000, you're only using a couple of lightweight transactions. So you can reduce it that way.
Yeah, instead of for each passenger.
Yeah.
Yeah. That's a question there.
I'm using pretty much the same lock. I do have, however, problems that he says, because we are trying to work in conditional split range when it happens, and it might happen to us. I was wondering if you have any way of reconciling a split brain condition when it happens. How do you mark this sort of things?
Now our solution, it would come back to the parts where we are not idempotent, I guess, and that's where we have the solution with our finite state machine, where we already marked all the parts in our application which we know which are non-idempotent. So in that sense, the finite state machines helps us, because it actually finds the orders or the transactions which are not completely processed in the non-idempotent part, and therefore we know that reconciliation is needed there. And if we can automate it, depends on the actions handled afterwards. So it's either a manual or automatic repair there, reconciliation. Okay.
Any more questions?
Oh, sorry. Oh, he was first.
Let's go back to locking again, but any reason why you didn't use Zookeeper or something like that? Locks rather than
Do you want to pick it?
You go first. Actually, I mean, active. Cassandra, we had it already there, and we reduced the need for using other technology, setting it up.
Yeah.
Zookeeper also, we're a bank, so setting up new software, setting it up, automated deployments, it's a lot of work. So it's also a conscious choice on what we already have.
Yeah, we just had some doubts about Zookeeper as well, because of Netflix also having doubts with Zookeeper themselves as well, and we take their IDs pretty seriously, we as ING. So we are actually investigating Zookeeper within ING. So it could be that we will move this to Zookeeper, but for now this works perfectly for us. We haven't seen any resilience scenario which we have tested which failed our tests based on what we have currently.
And also, in terms of your locking, so I guess you have the TTL on there. What happens if the process is trying to refresh it fails? And you've got no lock now. Does that cause you issues? Or I don't really understand your use case properly. But
It will not actually give us any issues, because we call it derailed carriages in that sense. So it will just stay off the rail for that sense. And we have a maintenance process, as Gary actually mentioned. We didn't go into detail there, but we can afterwards, which will pick up those carriages and will put them on the rail again.
So that's where the train management started helping, because then we can actually use all those words.
I want to ask about that too. How do you choose the TTL for the? Do you have different values for different types of locks, or do you have to refresh all the time? How do you...
Well, basically, the way we did it was the petition, depending on the petition size, you can decide how long you're going to give to read that petition. And then for every petition, you can just update it. Or you can decide, I think it's going to take 2 minutes for building up a file. It just depends on how important it is that that file needs to leave as soon as possible or how much time you have. So it differs per destination. And that's the reason why we use TTL, because then we can configure that on insert.
Are you only really holding like transactions and orders and things like that, or are you holding balances in there as well?
So you're asking for our use case here. We might tell you afterwards. We still don't want to jinx it, but you are close. Let's say it like that. Yeah.
Instead of the finite state machine, wouldn't it be easier and perhaps enough to use version counter as a zookeeper, or synchronize time with NTP, for example?
We wanted to use static columns and also keep track of how many states there should be and stuff like that. We were looking into all these. In the end, finite state machine works best because we can work out the state of where we are. And then also model. So our application is modeled with a finite state machine. So we actually have many uses for this finite state machine. And then just reusing that for this made perfect sense for our use case.
But it is a nice suggestion. So I think we will have a look at it. It does sound like a plausible, good solution, indeed.
We were even thinking of using both just to give us that extra protection if anything we missed. Anything else?
Does the finite state machine ever become a bottleneck or a single point failure?
Not yet.
No.
Yeah, that's it. We haven't experienced any bottleneck on the finite state machine as of yet, because that's actually also distributed across all the client nodes. It's also a distributed component in that sense. That's the beauty of it. That's it. Well, thank you very much. I hope you enjoyed it.